Hello and welcome to the next module on channel capacity and coding. We will start with the brief outline for today's lecture. We will revisit channel capacity and then focus our attention on Gaussian channels. We will then state and prove the information capacity theorem, and finally we will spend some time on the Shannon limit. Let us quickly recap what we have done so far. We have developed the general notion of the capacity of a channel. We had looked at symmetric channels and figured out how we can quickly compute the capacity for symmetric and weakly symmetric channels. We then looked at noisy channel coding theorem, and we took an example of a very simple error correcting code called the repetition code. So, very quickly, to refresh our memory, we have talked about the channel capacity C as the maximum of average mutual information between X on one side of the channel and Y on the other side of the channel, where the maximization is done over all input probabilities. And if you write it out, the expression for capacity looks like this. Please note some of the interesting properties of the channel capacity. Capacity is necessarily greater than or equal to 0, since the average mutual information is greater than or equal to 0. We also established that the capacity should be less than or equal to log x, where x is the cardinality, and similarly it should be less than or equal to log absolute value y, where this sign shows the cardinality of y. This simply comes from the extension of this average mutual information I x semicolon y should be equal to h of x minus h of x given y should be equal to h of y minus h y given x. So, this we have done already. A very quick recap on the noisy channel coding theorem, where we started off with a discrete memoryless source with an alphabet x with a given entropy h of x and producing symbols every ts second, and we established that if the source rate h of x divided by ts is less than or equal to c over tc, then we have a possible coding scheme where we can transmit information over this noisy channel which is unreliable, and at the same time reconstruct with arbitrarily low probability of error at the receiving end. On the other hand, if h of x divided by ts source rate is greater than this quantity which we will define as the critical rate, then it is not possible to transmit information reliably. This parameter we already defined is called the critical rate. Okay. So, this is what the noisy channel coding theorem tells us. Now, very quickly let us look at a very interesting and practical channel called the Gaussian channel. Okay. So, we now formulate the information capacity theorem for a band limited and power limited Gaussian channel. Please note, in the binary symmetric channel there was no notion of bandwidth. Did it figure out? Not at all. Where was the notion of power? Well, it was implicit in the channel transition probabilities, but it was never explicitly stated. But in real life, these are the two quantities we must deal with. Bandwidth, yes, we pay a lot of money. Remember the auctions for the wireless spectrum? So, band limited channels are a reality, way of life, and power. You do not have infinite battery power. You have to outdo your competitors. Your mobile phone should not drain out in the middle of your conversation. So, the channels are not only band limited, but they are also power limited. Gaussian we will talk about. So, let us have a very simple model. So, x of k is at the transmitter side and y of k is at the receiver side. What the channel does is it adds noise which is Gaussian, more specifically additive white Gaussian noise. Now the sub k represents the samples. So kth sample of the symbol gets added with the kth noise sample to get the yk output. So let us talk about this discrete channel, which is the time discrete channel with output yk at time k, and let us say the noise, sometimes it is denoted as zk in literature, but here we have denoted as nk, is drawn from a Gaussian distribution with mean 0 and variance sigma squared. Then we can write yk simply as xk plus nk, where nk is taken from this Gaussian distribution. Please note the first assumption we are going to make. We are going to make several assumptions. The first and foremost is that the noise nk is independent of xk. Okay. So this is the first assumption we make, and we will use this assumption to derive the information capacity theorem. Is this a fair assumption? Well, it should be. We have to really work hard to make it dependent. In general, the source is independent and the noise is generated independently in the circuit. So it is a good, fair, believable assumption that xk is really independent of nk. Now the problem before us is to figure out what could be the capacity of a Gaussian channel that we have defined. This Gaussian channel, we have already qualified it with being power limited and bandwidth limited. So band limited and power limited. Since the transmitter is usually power limited, let us put a constraint on the average power of xk. Remember, xk is what we are transmitting at time k. So what do you mean by average? Well, the expected value of xk squared is p. So this is the average power. It is possible that some of the symbols are being transmitted with lower power, some of them are being transmitted with higher power, but on an average we have the input symbols having a power of p. So the problem now translates to a constraint problem where we have to find out the capacity as maximization of the average mutual information Ix semicolon y given expected value of xk squared is p. As always, the maximization will be over input probability distribution. So this condition we have added. Okay. So what are the two things we are looking at? This power limited, which is putting this condition expected value of xk squared is p, and the probability density function of xk is this fx x. So this slide tells us that we are right now focused on the transmitter side, where the symbols are being generated with x k equal to 1, 2, 3, 4 up to capital K. So we proceed. So we start with the differential entropy, and we say that the average mutual information between xk and yk. So we are only focusing on the kth symbol is equal to hyk, because please note y is a continuous random variable and yk is a sample at time instant k. So small h representing the differential entropy. So hyk minus h of yk given xk. This is just the definition of this average mutual information. Now we have already assumed that xk and nk are indeed independent random variables. So we think a little harder and say that the conditional differential entropy of yk given xk. So we are looking at the second term on the right hand side. So the conditional differential entropy of yk given xk is nothing but the differential entropy of nk. Why? Because xk and nk are independent. So, if you go back to your original model, xk and yk are independent. So, if you want the uncertainty hyk given xk, right. So, if I know already, if I have been given xk, then the uncertainty in yk is coming from where? Only because of nk. So, h of yk given xk is nothing but h nk. So, we come back and say that intuitively given xk, the uncertainty arising in yk is purely due to nk. That is to say, h yk given xk is equal to h of nk. So, this is a very important assumption and it is based on xk and xk and nk being independent random variables. So, just because we have a strong intuitive feel, we could simplify this expression to I xk semicolon yk, average mutual information is nothing but the difference of the uncertainty h yk minus h nk. So, if you bring it closer and compare, we have got this second term h yk given nk being replaced by h nk. So, we are moving forward. Now, we have to make some more assumptions. See, if we assume yk to be Gaussian and nk to be Gaussian, then by definition xk is also Gaussian. Why do we have to do all of this? Well, these assumptions are being made to maximize the average mutual information in order to obtain the capacity value. So, we have to get some distribution of xk so as to maximize the average mutual information. But to make any comment about the distribution of xk, I must then talk about yk and nk. Now, nk is Gaussian by definition, and if we are assuming yk to be Gaussian, then xk to be also Gaussian. This is because the sum or even the difference of any two Gaussian random variables is also Gaussian. So, in order to maximize the mutual information between the channel input xk and output yk, the transmitted signal should be Gaussian. So, these are the logical steps to follow. So, what we can write now is that capacity. Now, we have said that we will maximize given the distribution of xk, but that xk which maximizes the average mutual information is Gaussian, and I will comment upon why is it so. So, then C is equal to the average mutual information x semicolon y under now two constraints. One is the power limited condition, that the average power of the symbols at the input is P, and again at the input we request that this xk to be Gaussian in order to write this capacity. So, this maximum value is gone, maximization is already done under the assumption that xk is Gaussian. So, that is the take home message here. So, we go a little bit further. If two independent Gaussian random variables are added, the variance of the resulting Gaussian random variable is the sum of the variances, right, because this is again the independence notion. So, let us quickly look at what we are doing here. So, we have this nice Gaussian channel where we have this xk and we have our friend today nk, because without this nk we do not have a case, and we have your yk. Now, we wanted to maximize the average mutual information in order to get the capacity. For that, the conclusion was that this xk must be Gaussian, This is Gaussian by definition, and sum or difference of two Gaussian random variables is Gaussian. So, this guy is also Gaussian. And why was this taken as Gaussian? Because we had this needs to be maximized, right, because capacity requires us to maximize this. This has to be maximized, and this is Gaussian, this is Gaussian. So, in order to maximize this, y should be Gaussian, this is Gaussian, it forced us to make x Gaussian. So, that was the general train of thoughts. Now, we do this independence thing further, and we know that the power here at the input, we have taken the average value to be p, and this is sigma squared, and this has a variance p. Then this is Gaussian, sum of two Gaussians, but we will ensure that this variance should be equal to p plus sigma squared. Okay. So, noise power can be written as n naught w, and therefore, we can write p plus n naught w. Very simple observation, the beauty of Gaussian distribution, right, and therefore, so we come back to the slide and say that it can be shown that the differential entropy of a Gaussian random variable with variance sigma squared is half log to the base 2 pi e sigma squared. Okay. So, you can show this, and what is very interesting is that if I give you two random variables with equal power, so variance, then it is a Gaussian random variable that maximizes the entropy. This is a very interesting part. So, what is the physical significance of this? Suppose I make an observation, some funny vibration is going on a bridge, or I am measuring some traffic condition, and I have no clue about what distribution to put in. Then the best bet is to model it as Gaussian, because Gaussian captures the maximum information. The entropy is maximum for a Gaussian random variable. That is why we chose Gaussian to be the distribution for yk and hence xk. And what is that differential entropy? Where for the Gaussian it is 1 by 2 log to the base 2 pi e sigma squared. So, for yk, which is nothing but the sum of xk and nk, the variances add up, and I have half log to the base 2 pi e, and instead of sigma squared, the effective sigma square is the sum of the two variances. So, p is the variance of x xk, and n naught w is the variance of noise, which is the noise power, right. So, very simply, no hard mathematics, we are combining intuition with a little bit of mathematics to get this differential entropy for HYK. Remember, our job is to find out HYK, then HNK, and find the difference, and that difference should be the capacity of this Gaussian channel. So far so good, we are trudging along. So, what have we found so far? We have this differential entropy of HYK as follows, and for the noise, which is also Gaussian distributed, our assumption, HNK is half log to the base 2 pi e n naught w, the noise power. Now, we come to finding the capacity, which is the difference, and we write it out explicitly. So, the expressions for HYK and HNK. So, we write it down as a difference. Now, log, difference of log is just tailor made for simplification, and so what we do is we take half log to the base 2 and then we take it common and we take the ratio. So, 2 pi e p plus n naught w divided by 2 pi e n naught w. So, this 2 pi e cancels out and I am left with p plus n naught w divided by n naught w, and we are left with finally 1 plus p over n naught w as the argument of the log. So, C comes out to be half log 2 1 plus p over n naught w, and clearly I must put the units of this, and it is bits per channel use. Okay. So, I am still uncomfortable because per use every time I use a channel, but suddenly I remember that I have to give an answer in terms of bits per second. I can always say okay every time you use the channel, but that does not really make much sense for the user. The user would like to know what is the capacity in bits per second, especially when we have introduced this notion of power limited and bandwidth limited. So, we have to take that last final step to change this bits per use, bits per channel use to something like bits per second. So, we need to find out how many times per second can I really use this channel. Okay. So, this point is bothering me still and I need to make a fix for this. So, what are we doing? We have so far derived that in terms of bits per channel use, capacity is half log to the base 2 1 plus p over n naught w, and since the log to the base is 2, the answer is in bits. We are transmitting 2 w samples per second because the bandwidth is w. So, we know that if we have a bandwidth of w, we can have in terms of the Nyquist sampling theorem, we can use the channel being used 2 w times in 1 second. So, then if we are using it fruitfully, then we can say that we have finally the last piece in the jigsaw. I have the answer of times per second the channel can be used. So, bits per channel use into use per second will give me bits per second. So, finally, I multiply this by 2 w. So, here it was half, when I multiplied with 2 w I end up with w log to the base 2 1 plus p over n naught w, and please note here we had bits per second and 2 w samples per second. So, if you use these two together I end up with bits per second. So, finally, I am quite comfortable with this notion of capacity, which is C w log to the base 2 1 plus p over n naught w bits per second. This makes sense. This I can go and sell my product. I can relate to bits per second. Okay. So, this is pretty much the capacity of a Gaussian channel. Okay. Now, this basic formula, even though we are saying it is basic, we will very soon realize how versatile it is and how much insight it can provide. This basic formula for the capacity of the band limited, power limited, additive wide Gaussian waveform channel was first derived by Shannon in 1948, and it is also known as Shannon's third theorem and also called the information capacity theorem. Okay. So, a quick recap of what we have done so far. So, we had this nice band limited, power limited channel xk at the transmitter, zk or nk, whichever notion you want to put in, it is added and I get yk, and the capacity we have derived as w log to the base 2 1 plus p over n naught w. So, we have introduced the notion of band limited and power limited. Now, it is a very interesting formula. Let us see what does it tell us. So, let us write it down. So, the first observation that we make is that this W is at two places. At the same time, N naught W is the noise power. So, this is effectively W log to the base 2 1 plus SNR. This is the signal power divided by the noise power, this is your SNR. It tells me that the capacity grows linearly with W. But logarithmically with SNR. This is an interesting observation. The capacity does not treat bandwidth and power equally. In fact, the capacity is partial towards bandwidth and is less partial towards in terms of giving importance to SNR. So, if you just plot it, and if you have this capacity on this axis, you have SNR versus your bandwidth. So, it kind of grows linearly with bandwidth. On the other hand, just I am superimposing to bring out the full import. It grows logarithmically with SNR. So, if I have money to put, I would rather put my money on bandwidth because it gives me a much better return in terms of the capacity than the SNR. In fact, if you look at the practical systems, the 2G wireless systems invested more in terms of SNR, right. But when we made a transition from 2G to 3G, for example, CDMA uses excess bandwidth and much lower power. So, it invested more in terms of bandwidth than power in order to get a better capacity. So, this is a simple way to justify why CDMA was chosen over the FDMA, TDMA systems when we transited from 2G to 3G. Okay. But there are many other implications in terms of bandwidth and power trade-offs. So, other thing that tells me is that we can trade off bandwidth for power in terms of performance, but we will come to that shortly. So, we go back to our slide and come to some of the interesting take home messages from the information capacity theorem. The information capacity theorem is one of the very important results in information theory. In a single formula, one can see the trade off between the channel bandwidth, the average transmitted power and the noise power spectral density. There is a one formula that links. Before this, there was no clear idea as to how to look at trade off between say channel bandwidth or the average transmitted power or how the noise power relates to the capacity. Right. Given the channel bandwidth and the SNR, the channel capacity can be computed. So, I can give you actual numbers. This channel capacity is the fundamental limit on the rate of reliable communication for a power limited, bandwidth limited Gaussian channel. So, it gives a theoretical limit on the rate of reliable communication. But it should be kept in mind that we have made some assumptions, and one of the most important assumption is that the transmitted signal must have statistical properties that are Gaussian in nature. This is not always true, and therefore, this is only a theoretical limit, but in order to achieve the capacity, X should tend towards Gaussian. Note that the term channel capacity and information capacity have been used interchangeably so far. So, we are sometimes talking about channel capacity of the Gaussian channel, sometimes we are talking about the information capacity of the Gaussian channel, well the theorem is called the information capacity theorem. So, let us look at a holistic view first. So, what are the current challenges? So, just for the sake of discussion, let us say we are going to design a wireless communication system, the next generation, maybe 5G, and what are the challenges in front of us. So, the designer has to look at several things, right from the coverage area to the performance in terms of bit error rate, frame error rate, delay, jitter, to the cost, security aspects becoming very important, and energy efficiency. It has a fancy name today called green communications. So, these are all the things that a person must juggle so as to get things right and sell the product in the market. But how does this relate to our information capacity theorem? Well, if you see, already we have how to trade off the power versus bandwidth versus performance. So, one thing that we have not really made it very clear explicitly is how the performance gets related, and that we will shortly link to. But before that, let us understand that these are the current challenges and the number of users you can support, what is the coverage you can provide, what is the performance you can give in terms of bit error rate to the different users, how much battery power will the user have to expend, how much bandwidth will you allocate to the user. All of this gets captured by one single formula given by the information capacity theorem. Now, we look at a very interesting thing called the Shannon limit. So, again this is the fall off from the information capacity theorem. Let us consider a Gaussian channel once again, which is limited both in power and bandwidth. Now, we wish to explore the limits of communication system under these constraints. So, let us define an ideal system, since we are looking at the limits, which can transmit data at bit rate RB, which is equal to the capacity. Please recall, capacity we have been finally able to nail it down in terms of the units bits per second. Okay? And this capacity, if you remember, your source rate should be less than this capacity so as to get reliable communication. Let us say we are running at capacity. So, RB, which is the data rate in terms of bits per second, is equal to C, right. So, this whatever we are going to derive under this condition will be the limit. If we go even 0.1 bits per second above this, we enter into the red territory where reliable communication may not be guaranteed. Now, we make another assumption, which is the energy per bit. Now, this is again a very practical thing. We always deal with energy per bit if you have to compare apples to apples in terms of higher order modulation schemes. So, the average transmitted power is nothing but EB into RB, because EB is energy per bit and RB is bits per second. So, we get say joules per second, which is watts in terms of the power, and RB has already been put equal to C. So, we have EB into C. So, P is equal to EB into C. Okay. So, now if you recall the information capacity theorem, we had the C equal to W. So, the W has been put on the left hand side. Now, we have C over W is equal to log to the base 2 1 plus, what do we have here? We had P over N naught W, but P we have substituted as EB into C. So, now the differently expressed information capacity theorem running at capacity is C over W equal to log to the base 2 1 plus EB over N naught C over W. Why am I doing this? I have got this C over W and C is equal to RB, that is equivalently RB over W at 2 places, and I have got EB over N naught as at 2 places. Okay. So, if we write it out, we can express it as please note C equal to RB in this case. So, it is equivalently RB over W equal to log to the base 2 1 plus RB over W times EB over N naught. So, you can always write this quantity as x, this quantity as y, and this quantity again is x. So, you have x is equal to, oh thank you, this is a y. So, we have y equal to log to the base 2 1 plus xy. So, it will be, so if I write it neatly, it becomes y equal to log to the base 2 1 plus xy, and this we should be able to plot, but we will have physical significance for both EB over N naught and RB over W. Okay. So, RB over W is the normalized rate, okay, and EB over N naught is kind of a SNR. So, if you go back to the slide, we can write now equation EB over N naught is equal to 2 C over W minus 1 over C over W. This is if you want to take 2 raised to power on both sides. So, now we plot the bandwidth efficiency RB over W versus EB over N naught. So, we have this RB over W which we designated as Y versus EB over N naught which we designated X, and whatever we get is called the bandwidth efficiency diagram. So, let us mark this axis first. On the x axis we put EB over N naught, this is what we put as x. On the y axis we have RB over W, and if you make the plot, you get this blue line as the Shannon's limit. This represents the condition that RB is equal to C. Anything below it will be RB less than C, anything above it is RB greater than C. So, we will come back to this diagram again, but let us look at this limit. this is called the Shannon's limit, which we will come very quickly. It is also a little counterintuitive. So, for infinite bandwidth, okay. So, what do we mean by infinite bandwidth? W is the bandwidth, infinite means this RB over W goes very low. So, I go down this limit. So, if you see, if I go down this curve tends to asymptotically become, it tends to some value asymptotically. This limit is the Shannon's limit that we will talk about. So, for infinite bandwidth, the ratio E b over n naught tends to a limiting value. E b over n naught as W tends to infinity is nothing but ln 2 is 0.693. In terms of dB, it is minus 1.6 dB. This is called the Shannon's limit. Now comes the counterintuitive part. This Shannon's limit is a fraction. What does it mean? This implies that for very large bandwidths, reliable communication is possible even when the signal power is less than the noise power. Now, if you do not understand the full import of it, let us draw and tell you that suppose for a certain case I have this as my signal, and suppose I have this as noise. Then when we add the signal and noise, we get something like this. What Shannon's limit tells us is, given infinite bandwidth, I should be able to recover the signal from this seemingly junk data. So, this shows that even if the noise power is larger than the signal power, if the SNR is minus 1.6 dB, okay, fine, still I can get reliable communication. And how reliable? Well, you name it, bit error rate 10 to the minus 10, you got it, but you give me infinite bandwidth. Well, how will I use that infinite bandwidth? I will use some kind of a stronger and stronger and stronger error control code to do this. Right? We come back to our slide. The channel capacity corresponding to this limiting value, right, with C with W tending to infinity. Well, what is it? It is P over n naught log to the base 2 E. This is a constant. What the capacity for infinite bandwidth is nothing but P over n naught. So, it is decided only by the signal power and the noise power. So, the capacity is completely determined by the signal to noise ratio for infinite bandwidth, and it just does not keep growing. So, it is not that I keep increasing the bandwidth and my capacity will keep increasing. This is a very interesting result if you ponder over it. So, just if somebody gives you a lot of bandwidth and keeps giving you more and more bandwidth, it does not mean that you can keep increasing your capacity. So, let us look at that Shannon's limit and this plot for this RB equal to C condition once again. So, this is the capacity boundary. So, this blue line is called the capacity boundary. On the x axis again you have EB over n naught, on the y axis you have RB over W bandwidth. Here sometimes we denote bandwidth by B, but it is RB over W, and what you have is this region, this red dots, which is RB greater than C. RB greater than C means that reliable communication is not possible. You cannot limit your error rate. So, it is all over this place, right, but above this blue line. So, this is your RB greater than C. On the other side is the region where we can design practical systems where RB is less than C. Okay? And again below this blue line, all of this region, right, is your RB less than C. Here we can have reliable communication, okay, with arbitrarily low probability of error, and this blue line, which is the capacity boundary which separates this region for practical communication and the other region. So, basically the bandwidth efficiency diagram shows the trade off between the quantities RB over W and EB over N naught, and in terms of the probability of error. So, for designing any communication system, so the basic design parameters are the bandwidth available, because you pay money for it, the SNR, well, that will decide the battery life and it is expensive also, and the bit error rate. Okay, these are the three things we must juggle. So, let us now summarize what we have studied so far. We started off revisiting the channel capacity, then we jumped directly to the Gaussian channel, which is a practical channel, has far reaching consequences. Then we looked at the information capacity theorem, we stated and derived the information capacity theorem, and we understood what do we mean by the Shannon limit. That brings us to the end of this module.